Welcome back to CS103 Machines, Languages and Computation. In this lecture we're going to look at two different views of these objects that we call functions. One of them is going to be a computer science view, the other a view from mathematics. So let's have a look at what this is about. So far we've regarded functions as being input-output boxes. Sausage machines. In other words, you stick your sausage meat and your sausage skin in one side and sausages come out the other because there's some machinery in the middle. So the input goes into your machine, then there's some machinery, that's the algorithm, and then some output comes out. That's what we've viewed functions as so far. But the mathematical view of functions is rather different. It's actually an association between two sets. So a function is a set of pairs. So it's a set because it's got curly brackets around it. If the input value is x0, this says the output value should be y0. Notice that the function, the mathematical function, doesn't tell you how to do the computation. It just says that for x0, the output should be y0. For x1, the output should be y1. For x2, the output should be y2, and so on. So it's a bit like a specification for an algorithm without actually telling you what the algorithm is. The x variables in a mathematical function are chosen from a set called the domain. So all of these x variables are chosen from a set called the domain, and the y variables for a function are chosen from a set that we call the range. So the full set of all the y variables for this function, that's called the range. Now the association is simply this set of pairs, and it can have some sort of sense to it. You'll see some examples where there is some sort of sense to it, but it can just be an arbitrary association between members of one set and members of another set, and you'll see examples of that too. So a set of pairs, and later on in the week I've got a video for you where you can visualize these using what are somewhat strangely called potato diagrams. You'll see that in the video shortly. So let's have a look at some example function. For each domain value, that's the input value, there must be one and only one value in the range. Otherwise, this relationship is not a function. So here's a function. 1 maps to 1, 2 maps to 4, 3 maps to 6, 4 maps to 16. As I said, the association can have some sort of sense to it or not. And you can see that for this one, the association does have some sort of sense to it. If I gave this to you as a specification for an algorithm, you'd say, I'll take in the input and I'll square it. So here, the domain is 1, 2, 3, 4. That's the set of all possible input values. And the range of this function is 1, 4, 9, and 16. That's all the output values. Here's another example of a function. 1 maps to 0, 2 maps to 1, 3 maps to 0, and 4 maps to 1. So for each and every member of the domain, there is one and only one member of the range that it maps to. So here, the domain is 1, 2, 3, 4, and the range is 0 and 1. That's all the possible output values for this function. Let's look at this example though. 1 maps to 0, 1 maps to 1, 2 maps to 0, 2 maps to 1. Think about why that's not a function based on what you can see on this slide. Okay, so the answer is, the reason this isn't a function is that the value 1 is mapping to two values. There can only be one output value if this thing is a function. So it says there must be one and only one value in the range, and that's not obeyed by this. This is just a general purpose relation between two sets, but it's not a function. Okay. One of the things that we can do with a mathematical function, so when we're presented with it, we can try to come up with an algorithm for automatically computing. And I'm going to call that a mapping, or sometimes a computable mapping. So here, this function, this mathematical function, 1 to 1, 2 maps onto 4, 3 maps onto 9, 4 to 16. The algorithm, the computational mapping, could be take the input value and squared it. In other words, f of x is equal to x squared. Here's another example. 1 maps onto 0, 2 to 1, 3 maps onto 0 and 4 to 1. Well, an algorithm for that would be if the input number is even, you output 1, and if it's odd, you output 0. So in other words, it's just basically it's a test for evenness. Now, if you've got a finite function like this, you can of course always just enumerate all the cases. You just say if the input is 1, return 1. If the input is 2, return 4. If the input is 3, return 9. If the input is 4, return 16. You can do that if your function is finite. You can always do that. But if your function is infinite, and we're going to move on to infinite functions shortly, then you can't always do that. One of the things that we can do with these algorithmic mappings is that we can compare the size of sets. And this is really useful. It's going to be really useful to us later when we're doing the big proof, the one of non-computable functions, which I'll be getting to probably next week. So consider these two sets. A is the set 1, 2, 3, all the way up to 1000. And B is the set 1, 3, 5, all the way up to 2001. So it's the odd numbers between 1 and 2001. What I'd like you to think about is one set bigger than the other, or are they the same size? And if one is bigger than the other, which do you think is the bigger set, A or B? Or are they identical? Now we could count the elements of each set, but that'd be a bit tedious. So you could count up to 1000 and then count all the elements of B one at a time. But instead, what we can do is we can make an algorithmic mapping from elements of one set to elements of the other set and see if that mapping accounts for elements of both sets. So this is an exercise for you. I'd like you to try to make an algorithmic mapping that takes as input a member of the set A and produces as output a member of the set B. And then once you've got that algorithmic mapping, see if that actually accounts for all elements of the set. And I'll give you the answer in the tutorial this week.